In the last video, we defined what the halting problem was as a language problem, and then we showed that it was semi-decidable by building a simple Turing machine which semi-decided the language. In this video, we're going to show that it is not decidable, and that is going to have a number of important repercussions, but the main thing is that it means that we cannot build a program which takes as input other programs and their inputs, which will always halt and tell us whether or not the given program will halt or not. And that means that we can't go through and build simple debugging tools that'll tell us when our programs are going to loop forever, because it is not solvable in general. So for this, I'll need you to remember two important things. Firstly, the language H, which is the halting problem language. And that is the set of encodings of Turing machine and input string pairs such that the Turing machine halts on the input string. And I also want you to remember what the definition of a deciding Turing machine is. And a deciding Turing machine is one that always halts and which accepts if and only if the string is in the language that Turing machine is deciding. Now that means that if the string is not in the language, that it must reject, because it is not able to do anything other than halt on any input. The proof that we're going to do to prove that the halting problem is not decidable is going to be a proof by contradiction. So the first thing we're going to do is assume that it is decidable. If a language is decidable, then there must exist a machine which decides the language. So let's call the machine which decides the language H, that we are assuming exists, halt. So that machine is given a string which encodes a Turing machine and a string which encodes the input to that Turing machine as its input. And if that Turing machine that it is being given halts on the given input, then this machine must halt and accept. And otherwise, the machine must halt and reject. So remember, for this to be a deciding Turing machine, it has to halt on all inputs. And if the input is in the language, and the language an input is in the language H, if that machine halts on that string, then our machine must accept. And otherwise, the machine must reject. So that means that this machine, a description of the machine like this, must accept. If that machine does exist, then we can also define another machine, which we call trouble here. And the definition of that machine is it is given an input string, and in this case we're going to talk about these input strings as being encodings of Turing machines, but it doesn't really matter what they are. But it is given an input string, and it runs halts on the pair of that string doubled. So if we ran trouble M, it would run halts M. So it would ask if that encoded Turing machine halts on its own, on itself as input. If halts accepts that input, then the machine that we're defining trouble will loop forever. And otherwise, the machine that we're calling trouble will halt. So I want you to just stop on this slide for a second and just look through these two, because whilst they're very simple definitions of Turing machines, it can take a little while to wrap your head around it. And on the next slide, I'm going to ask you a few questions about what happens when we run trouble on a particular input. So here are the descriptions of the two machines that we've talked about. I want you to pause the video once I've finished asking this question and decide what happens if we run trouble on the encoding of itself. Will it run trouble on the encoding of itself as a pair? So on trouble encoded. Will it run halts on that pair of encodings of itself? or will it just run halts on the encoding of itself once? So pause the video here and decide which you think will happen. So the answer is it runs the second. Remember that this here is the input W, and trouble runs halts on the pair WW. So that is this answer here. So the second pair of questions I'm going to ask you is, what does it mean if halts accepts the pair trouble trouble? Does it mean that trouble halts on itself as input, or does it mean that trouble does not halt on itself as input? And what does it mean if halts of the pair trouble trouble rejects? Does it mean that trouble halts on its own input, or does it mean that trouble loops forever on its own input? So pause the video and then I'll show you the answer. So the answer is that if halts exists and correctly decides the halting problem H, then if halts accepts this pair, then trouble must halt on itself as input. And if halts rejects the pair, then trouble must loop forever on itself as input. And here you might be able to start seeing where the contradiction occurs. Because the problem is that by definition, if this accepts, we have defined that trouble will loop forever. And if halts rejects on the pair as input, then we are in this case here where trouble is defined to halt. But if halts exists as a deciding Turing machine which decides this problem, then this must be the case. And these things contradict each other. So there is no way for halts to exist where trouble is not a contradiction. So to sum it all up, if halts exists, then trouble exists. And if trouble exists, we can run it on itself as input, which will run halts of trouble, trouble. But if halts accepts this pair, then trouble by definition does not halt. But halts only accepts an input if the machine running on the input string halts. And if our machine halts rejects this pair, then by our definition of trouble, trouble must have halted. However, this Turing machine halts has decided that trouble does not halt on that input. So we can see that this is a contradiction. And since the only thing that we assumed was that halts decides the language H and exists, then that assumption must not be correct. There must not exist a machine which decides the language problem H. So don't worry if you're very confused at this point. This will be gone over in lectures as well, and also down the bottom here I've posted a YouTube video which goes through this in a lot more detail and maybe in a more intuitive manner. So you can look at this video and then you can go to the lecture and Nassimul will explain the problem all over again. But basically you should understand that through our proof by contradiction, we now know that the language H is not in the set D, which is the set of decidable languages, which means that there is no Turing machine, there cannot possibly exist a Turing machine which will always halt and will answer yes or no to whether or not a machine halts on an input string. One of the things we are going to use is this fact here we are going to use repeatedly as a basis for proofs that other languages are or are not in the set D. So it's important that you understand and are happy with the proof that the halting problem is not decidable, because it will be the basis for a large number of other proofs that you will have to do in this course. And these are going to be reduction style proofs. And whilst they are complicated, they don't involve a lot of algebra or other mundane mathematics, and instead they involve a lot of logic and reasoning. So this is the last video that you'll see from me. I just wanted to say thank you for taking this course. I've had a lot of fun producing these videos for you guys, and I always have a lot of fun running the tutorials for you. I always get a lot of interesting questions from people. One thing I would like, if you have appreciated these videos, or even if you have hated these videos, is for you to give me any feedback you possibly can, because it's through your feedback that we can take the course and modify it and make it better for future students. So at this point in the course, there's not much we can do to make it better for you, but if there have been problems that you think could be fixed, or things that you think could be better, or just things that you want to say that were great and you would really like them to continue for any other students in the future, please let us know. Thank you.